All right. Buffer solutions. What's a buffer system do? Buffer systems function to minimize changes in pH. If excess hydroxide or acid or an excess base has been added into the buffer system. The composition of a buffer system generically is a weak electrolyte along with a salt of the weak electrolyte.
God bless you.
This means you can make a weak acid buffer. You can make a alkaline buffer. You can make buffers that are neutral. An acidic buffer might be composed of acidic acid and its salt sodium acetate. Alkaline or basic buffer might be an ammonium hydroxide and ammonium chloride. You can also have mixtures of salt systems, which we call the basic end of this, to adjust the pH. You can have, say, an acidic acid and a sodium bicarbonate system. And we call that a mixed buffer system. The presence of the common ion, if you look at this, you'll see me underlining in each case, and this is not a common ion, but it's an anion that would inhibit or retard the shift of equilibrium and the presence of excess acid or excess. It is important that we focus here on specifics of buffer systems, because this is one topic that you could spend years on. So I'm going to be very specific about what you need to learn relative to buffer systems. Okay, of course the composition, you know, if I give you HOAC and AOAC, yeah, that's a buffer, an acidic buffer system. But what kind of calculations are usually associated with this? Determine pH of buffer mix. That's one calculation you will need to determine. Determine pH after adding quantities of OH base or H acid. Like that. Method of buffer preparation. That's enough. Okay. Okay. Now, the first thing we need to do is determine the pH make a buffer system and determine its pH. What I'm about to share with you is what I call a 50-50 buffer. Essentially, it is a system whereby the acid concentration and the salt concentration are equal. Or base concentration equal to the salt concentration. We're going to use acetic acid. So our buffer is going to be in a aqueous solution, but it's going to have a composition 0.10 molar acetic acid plus 0.10 molar N sodium acetate, common ion. The conjugate base of the salt, OAC, is going to be referred to as the base in the work we're doing. To analyze the pH of one of these, you have to use the common ion effect approach and apply it to the ICE table and such. Initially, the change in concentration, I'll bring this on up, change in concentration at equilibrium. Okay? Essentially, we're showing a 0.1 molar and 0.10 molar OAC, and we start before ionization, as you know, is 0. Equilibrating the system will decrease the acid and increase the salt and provide some hydronium ions to the system. And you can drop the X down here because it's still very, very small compared to the amount of primary compounds we have. So it's 0.10 molar X, 0.10 molar. Okay. So I need to calculate what X is. Of course, it is the hydrogen ion concentration. It's calculated from the Ka expression. And what's unique about this, when you substitute the equilibrium row in there, let me put the Ka is 1.8 times 10 to the minus 5. Okay. When you substitute, you have the following. Right here, notice the concentration of the salt in the numerator and the concentration of the weak acid in the denominator are equal. So this and this will fall out, and the Ka value equals the hydronium ion concentration. So the hydronium ion concentration, being the Ka value, is equal to 1.8 times 10 to the minus 5, allows us a pH value of a minus log of 1.8 times 10 to the minus 5. So we have a pH of 4. With this is a table of acid ionization constants, if you can see it. Here is acetic acid. They listed it 1.7. But if you took acetic acid and the salt, this is the salt over here. Well, is it? No, that's just the formula. There's one page over there that gives you the anion over here. But anyway, if you mix a buffer system out of acetic acid and a 50-50 salt and acid, all you have to do is take the log of that number. And that'll give you the pH. Or any one of these going all the way down, you've got the pH of a 50-50 buffer solution. So if I ask you on a test and give you a bunch of real hard-looking problems, and boric acid has a Ka of 5.9 times 10 to the minus 10, if I had, 10 to the minus 11 up there, what are you going to do? Punch it in your calculator, hit log, and you're through. Okay? Okay, I want to look at what happens if you titrate a weak acid and a strong base and buffer system against a strong base. So, question, say, for number 1 is HOAC titrated with NaOH, like that. And of course, you are setting up the acid in the beaker, and then you're adding sodium hydroxide. Well, if the acid's in the beaker, it starts at around pH of 3 something, and follows a trend of a weak acid, as shown. Now, this is an unbuffered system. However, if you have a buffered system that you were trying to titrate, say an HOAC buffer plus sodium hydroxide, how will that affect? So as you add the excess base into the titration, what you would observe is a trend like this. Very slow change in pH, and then at some point downfield, if you would, it will break the buffer and show a same equivalence point at the as acetic acid would normally show. But the essence of the buffer system is to minimize changes in pH when large quantities of acid are placed in it, and it shows here in the titration trends that it resists the loss of basic structure of the acid against the salt. Problem 1 up here is calculate the pH of the 50-50 buffer. That is for HOAC and OAC at 0.1 molar. Well, the hydronium ion concentration, as I've shown you earlier, is equal to the Ka value of this ionization of the acid, which is 1.8 times 10 to the minus 5. So this would give pH to equal minus log 1.8 times 10 to the minus 5. Okay, so let's keep that in mind as we go into the next one. I'm going to need. Okay. The essence of this is to ask yourself, how is the buffer chemistry going to remove the excess? How does the buffer chemistry remove the excess acid? Well, to see this, we'll start with the equilibrium of the weak acid right here, and establish in our minds the initial condition is a 50-50 buffer, meaning that it has equal concentrations of acid and conjugate base here, and has equilibrated, okay, to provide a hydronium ion concentration equal to Ka. In this case, 10 to the minus 5 molar in hydronium ions. Now we're going to add to that a 0.01 molar HCl. 0.01 molar HCl. Well, that's going to be adding 0.01 molar in hydronium ions, right? Because it's a strong acid. So if we look at our equilibrium, this is what happens. We find that we adding the excess hydrogen will tilt it to the right. So what has to happen? The reaction has to shift to the left. And as I'm showing it to you, when it does shift to the left, you have to decide, well, what's the concentration of HOAC doing, and what is the concentration of OAC doing? So as this shifts to the left, so you're starting with a 0.1 molar, and you throw in this extra acid. Well, this thing's going to tilt, and it's going to continue to shift to the left until all the excess acid is removed. So the only way you can do that is for the excess or hydrogen that's present to combine with the OAC. And as it combines with the OAC concentration will go down in an amount equal to what you threw in, and this will go up in an amount equal to what you put in. Excess acid. So when you're working a problem like this, you have 0.10 molar here, 0.10 molar here, and we're going to say this is so small is irrelevant compared to what you just put in. As far as hydronium ion, 10 to the minus 2 versus 10 to the minus 5, well, we'll just assume that starts out at 0. Your changes are what I marked in orange. Watch this closely. We have to get rid of 0.01. The chemistry is going to do that. The chemistry is going to remove the 0.01 by combining the 0.01 molar, the hydrogen, with the OAC, so that concentration is going to go down over here. We're starting with a 0.1. It's going to go down. So what I want to do in the change is subtract what this chemistry is taking out because it's shifting to the left. Well, how about over here? It's increasing. And to reestablish the new equilibrium, we want to add that amount to that side because it shifts back to the left. And at equilibrium, we have a new equilibrium which consists of 0.11 molar in acid and a 0.09 molar base. And a new equilibrium is established right here. So now we have to determine what X is in our new equilibrium, which will be the hydrogen. Take the minus log, and we have the new pH. So with the expression, Ka expression now, it is still used H plus times OAC minus over OAC, and this will give us a hydronium ion concentration to equal Ka HOAC over OAC minus, and that's 1.8 times 10 to the minus 5 times 0.10 11 molar. That's our new molarity here. And 0.09 molar now in the base. So our new hydronium ion concentration is 2.2 times 10 to the minus 5. And we threw in the acid. So with that in mind, we can calculate the pH minus log hydronium ion minus log of 2.2 times 10 to the minus 5, and our new pH is 4.65 after removing the acid. The pH of the 50/50 buffer was 4.74. Now we're at a 4.65. Now, one truism here, factoid, is that when you put an acid into a buffer system, it will shift in the acid direction. So when you finish your calculation, be sure you're in the acid direction if you do this. So okay, here is our 50/50 buffer. Has a pH of 7.47 before we add anything in. Now, adding 0.01 molar sodium hydroxide is, of course, strong base. The same thing as adding 0.01 molar in hydroxide ions into the system. Again, the chemistry of the buffer system has to eliminate 0.01 molar in base hydroxide. The way it does that is that the OH excess reacts with the hydronium ion to produce water. So you will have, if you have the excess hydroxide in here, it's going to start taking out the hydrogen, and you can find it acting like this. One way to look at it. You've got a hole here. It's getting lighter. Where the hydronium ion is removed from this side of the equation. One of the seesaw buddies jumped off. So when we look at the equilibrium effect here, we'll find it will tilt to the left. The issue is the reaction will need to replace the missing hydrogen in here to reestablish the new equilibrium. So when we look at our equilibrium, who's going up and who's going down as the OH is being removed? Well, as we shift left, this concentration is going to be going down, and the conjugate base concentration is going to be going up until we get to the new equilibrium. So in setting up your problem, zero point 0.10 on this end. Now this is going to go up this time, so we want to add the 0.01 to the right side or the base side and subtract the 0.01 from the acid side this time, leading us to 0.09 molar and 0.11 molar on here, and of course we'll get the new hydronium ion concentration now based on the calculation we use for this effect. So using the Ka equals hydronium ion, OAC, and HOAC. Again, we solve for the hydronium ion, and we have Ka, HOAC, and OAC, and this will give us 1.8 times 10 to the minus 5, and the 0.09 goes on top this time, and 0.11 goes there. It will all be in moles per liter, and we will have the new hydronium ion concentration. 1.47 times 10 to the -5 for the new hydronium ion concentration. And so the problem here winds up with a final pH. All I have to do is hit my log button, and I have 4.83 after adding the base. This is before, and this is after adding the base. Notice it went up. Of course, you add a base, it's going to go in the base direction. Yes? Okay. Now, looking at an alkaline buffer, we make a 50-50 alkaline buffer, and the outcome is a Kb equals to the hydroxide concentration, and then you calculate the pOH and subtract it from 14, you get the pH of your alkaline system. So an alkaline buffer might be a 0.10 molar ammonium hydroxide and a 0.10 molar salt of ammonium chloride, like that. Okay, now what we're essentially doing is we're mixing a 0.05 molar NH4OH and a 0.05 molar NH4Cl. Everybody understand it? You literally, instead of 25 mils, we got 50 milliliters, but we threw the compounds in with them, which diluted them to 1/2 of the original value. So when you set up your equilibrium, always set it up around the weak acid or weak base. So we're at initially 0.05 molar hydroxide and 0.05 molar in this, and we could go to the Kb value. Now in this particular case, when the concentrations are equal of the salt with the weak acid or base, then in this case the hydroxide ion concentration will equal to the Kb value, which is 1.8 times 10 to the -5. And we know that pOH is minus log of the hydroxide ion concentration. The pH now is 14 minus pOH, which gives you a 9.25 for the buffer mixed in. Okay. Yeah. 15 milliliters of the sodium hydroxide in the first case. Okay. Now, you need to calculate the molarity of the sodium hydroxide in the 50 mils, so that's 50 plus 15. So everything's changing. So you have to readjust not only the amounts of sodium hydroxide, but you have to adjust the acids and bases also in your buffer system. They're no longer at the 0.05 here. All of a sudden you've got 65 milliliters right here. So you need to go back and calculate, well, how many moles does this represent? So now you have so many moles using molarity times volume in liters, okay, divided by the new total volume you have to deal with, which is 65 milliliters now, and set up an entirely new equilibrium, like you're starting with a new base salt equilibrium. Let's start out and compute what our new ammonium hydroxide concentration is going to be when we drop 15 milliliters of solvent on it. Okay? So we're starting with 25 milliliters, initial moles is equal to 0.025 liters times 0.10 molar, give you moles of NH4OH. And the same thing with the ammonium chloride. Because they both started at 0.1 and we mixed 25 mils of it, okay? How many moles do you have if you happen to have it in 25, 30, 40 mils? Okay, or it's going to add the 15 in the total. No, okay. This is all we can do here. Okay, so move that over. 0.0025 mole NH4OH and NH4Cl. Now we want to drop this into the final solution. What's the final solution mix here? Okay, we have 50 plus the 15, that's 65 mils. So the adding 15 milliliters of the 0.01 molar sodium hydroxide to the system gives me a 65 milliliter solution now. So now what's your concentration of the NH4OH and NH4Cl? Well, if we have 0.0025 mole of each of them and 0.065 liters, moles per liters is your concentration. So in our equilibrium up here, we started here at 0.05 right here. That's before we threw in the moles of OH. So when we throw in the moles of OH to load up this side over here, it's going to also be loading up with some extra solvent. So this 0.05 is going to be diluted by the addition of 15 mils of the contaminant, the OH that we're throwing in there. Yes? And when we take that into account, we're now at 65 milliliters. We have to calculate the moles that we start with. Now this is before the interaction. This is the new before issue. Okay. So now we have an initial NH4OH, NH4 plus an OH over here. So it's now 0.039 mole per liter and 0.039 mole per liter there. I don't care what its hydroxide in that row is, because we're going to throw it, we got to take out the base that we're putting in there. Well, the base that you're putting in is 15 milliliters of 0.01 molar sodium hydroxide. And that's 0.015 times 0.01 mole of the sodium hydroxide, which is 0.0015 mole sodium hydroxide, and the concentration of sodium hydroxide equals the hydroxide concentration, and that is now 0.0015 mole in 65 mils, or 0.065 liters. So it's 0.023 molar in the sodium hydroxide. So I've gone through and recalculated each one based upon a 65 milliliter solvent volume. If you'll do that, you can keep up with this stuff. It can get real tangled. So starting with an 0.39 molar, we have to remove 0.023 molar in extra OH. So if I'm putting the extra OH into my equilibrium here, there's your extra OH. What's your seesaw going to do? You see me yet?
Tilt to the right.
So we're low on this end. So in order to get back to the balance, we have to shift to the left in this equilibrium, which means that this is going to be taken away from this and added to this one. And of course this goes down to the new, right there, hydroxide concentration. Okay, so the Kb expression for this equilibrium is given here, right here, and we need to solve for the hydroxide concentration, which will lead us to the hydronium ion concentration and consequently the new pH, which is the objective. So Kb is 1.8 times 10 to the minus 5. The ammonium hydroxide is now 0.062 molar divided by the salt or the ammonium concentration of 0.016 molar, giving 6.7 times 10 to the minus 5. And so from here, you could use the Kw expression for water and then divide this into 10 to the minus 14 and get your hydronium ion concentration if you wanted to do that, or just take the log of it. Okay, so this is just another pathway. Also has one more in it. I'm going to leave that one for you to do. Okay? Go through, see if you can calculate it. Which direction would you expect the pH to shift? It's going to go down. Should be below the buffered 9.25. So when you have the initial Well, this one, you calculate what would all right, I got one for you here. Let's say this is the buffer system, right here. What's the pH of this system? Now the point, the 0.05 came out 9.25. What's this one going to be?